So section 5.2, what have we learned so far? The two words are still up there. What have we learned so far? Perpendicular bisectors and angle bisectors. Those are two theorems we learned so far. Okay? We are adding to those two theorems. Okay? What do you think the term concurrent means? Take a guess. What do you think concurrent means? If I tell you two lines are concurrent to each other. I heard same distance and I heard overlap. You're very close. Okay? If I have these two lines are concurrent to each other, they meet at a same point. Okay, so write that down on your notes. Concurrent means meet at a point. Okay. So, what do you think point of concurrency means? If concurrent means they meet at a point, what do you think point of concurrency is? Where they meet. Yep. Where two lines meet. Okay. So today I'm going to use that word a lot. Just know that it means that they meet at a point. Okay. And that point is called the point of concurrency. Okay. Okay. So first thing I want to talk about is concurrency of perpendicular bisectors. Okay. First, we need to understand what all three of those words mean. What does perpendicular bisector mean? Perpendicular means? Cross at a 90-degree angle. What does bisector mean? Splits it in half. Okay? What did we just learn concurrent means? Where they meet at a point. Okay? So, this is going to be one big theorem that I want you to write down. If perpendicular bisectors meet at a point, I'm going to say meet at the same point. Again, what's that point called? Point of concurrency. Yep. Okay, if perpendicular bisectors meet at the same point of concurrency, comma, then the lines from the point of concurrency to the vertices are congruent. That is the concurrency of perpendicular bisectors theorem. Okay? What I want you to realize is it is an if-then. So if perpendicular bisectors meet at the same point, then the lines from the point of concurrency to the vertices are congruent. Don't worry, I'm going to put a picture with it. Okay? Next to that, I want you to draw a triangle. Doesn't matter what that triangle looks like. Okay, I want you to draw a triangle. Let's break this apart. How do I draw perpendicular bisectors?
Oh, just cut it in half.
Right, cut each side in half. So, I want you to draw, well, how many sides are there to a triangle? Three. I want you to draw three perpendicular bisectors that meet at the same point. Okay? So, for example, I'm just going to draw this one. This one. Again, your pictures don't have to be perfect. Okay? And this one. How would we know they're perpendicular bisectors? What do they do to the sides? They split them in half, right? So I would know this side is congruent to this side. This side's congruent to this side. This side is congruent to this side. We know that from section 1, right? That's the definition of a perpendicular bisector. Okay? So if those perpendicular bisectors meet at the same point, do you agree they meet at the same point?
Yeah.
Okay? That point right there is the point of concurrency. Okay? Then the lines from the point of concurrency to the vertices are congruent. Okay? We know where the point of concurrency is at. Where's the vertices?
Where they meet like the other lines. So
Where two lines intersect, right? So if I label this triangle ABC, where are the vertices?
in
A, B, and C are the vertices, right? So those lines that end up being congruent from the point of concurrency to the vertices. Okay, well, how many vertices are there? 3. So these lines from this theorem are said to be congruent to each other. So again, if perpendicular bisectors meet at the same point, which they do, okay, then the lines from the point of concurrency to the vertices are congruent to each other. So if you look at, go ahead and flip your notes to example 1. It has part of it drawn for you of that theorem, okay? It kind of looks like my example here. Does it have perpendicular bisectors? How do you know they're perpendicular bisectors? They have a right angle, and Kenzie, what'd you say? The sides are congruent. So we know those 3 lines are perpendicular bisectors. Okay, what do we care the most about them? Where they meet, right? Put a dot there. We care about that point right there. Okay, since they meet at a concurrent point, what did we just learn is true?
Then A, B, and C are all congruent with the vertices.
Right. So for a line, make a line from the point of concurrency to the vertices. Okay, what do we know about all 3 of those lines? They are congruent to each other. So, I'm going to say if BP is 6, what is PC?
It's also 6.
Also 6. What is AP?
6.
Also 6. Okay? And again, with the perpendicular bisector theorem, okay, if this side is 4, what's the other side?
4.
This one's 4. Does that mean this one's also 4? No, because it's different congruent markings. Okay, good. Okay, now we're going to talk about concurrency of angle bisectors. Okay, so we just talked about concurrency of perpendicular bisectors. Now we're going to talk about the angle bisectors. Okay, from lesson 1, would you say that perpendicular bisectors and angle bisectors are fairly similar to each other?
Yeah.
What's the one difference?
Yeah.
One's for angles and one's for sides. Okay, similar idea here. Okay, so here's our theorem for concurrency of angle bisectors. If angle bisectors meet at the same point, what's that point called? Yep, point of concurrency. So if angle bisectors meet at the same point of concurrency, then the lines from the point of concurrency perpendicular to the sides of the triangle are congruent. Now, yes, this one is a little more wordy than the perpendicular bisectors, right? But if you broke this down, you know what all of those different words mean, right? Okay, so let's put it with a picture. Go ahead and draw a triangle. Again, doesn't matter what the triangle looks like. Again, what's nice about this one, it's a if-then. So if this is true, then this is true. So let's break it apart. If angle bisectors meet at the same point, well, what's an angle bisector? Splits an angle in half, right? So draw lines that split all 3 angles in half. How can you mark that it split those angles in half? Congruent markings, yep. So all 3 of these pairs are split in half. What is that point in the middle? Point of concurrency. Okay, that's the most important part. All three angle bisectors meet at a point of concurrency. Okay, that just means they meet at a similar point. Okay, now moving on to the then statement. Then the lines from the point of concurrency perpendicular to the sides of a triangle. How do we draw that? Point of concurrency perpendicular to the sides of a triangle. So from here to here, what does perpendicular mean? 90-degree angle. Does that mean that's a perpendicular bisector? No. Okay, if it was, it would say perpendicular bisector here. Okay, it's just wanting a line perpendicular to that side. Okay, so draw one of those to each side. So from the point of concurrency to the side of a triangle. Okay, so it says, then the lines from the point of concurrency perpendicular to the sides of the triangle are congruent. So what can we assume about those three lines? They're congruent to each other. Okay, do you kind of see how this theorem, concurrency of angle bisectors, is similar to concurrency of perpendicular bisectors? They're kind of just opposites of each other, just like they were in lesson 5.1. Okay? So what this says is if these angle bisectors are meeting at that concurrent point, if this perpendicular line is 5, what is this one? Also 5. What's this one? Also 5. Okay, good. Okay, so directions are going to be very important. Okay, it says if QP is 3x plus 1. Okay, so I'm going to put in is 3x plus 1. I'm going to simplify that. 3x plus 3. And RP is 5x minus 3. Okay, ignore the rest. It says KP and LP are angle bisectors. Why do we care about that? Think of the concurrency of angle bisectors.
R and Q are going to be.
Right. These two meet at what? What's this point called? Point of concurrency. Okay. Since angle bisectors meet at that point, what do we know about these perpendicular lines? They're congruent to each other. So how can we solve this? Set them equal to each other, just like you've been doing. Okay, 3x plus 3 equals 5x minus 3. How do I solve that? I don't know what I heard, but I'm going to do this. Okay, does it matter the way you do it? No. What do I do next? Add 3. What am I going to get for x? 3. Okay. You might hear questions of what is the length of PM from JL. So like this length right here. What would that length be? How could we figure that out?
Wait, no.
We would have to plug it in, right? Okay, just like we've been doing in section 1, we would plug this 3 into here. So we get 5 times 3 is 15 minus 3, 12. Okay, so similar things are going on. It's just applying different theorems. Okay, let's look at this one together. This one says the measure of BAF, is that talking about an angle or a side? Angle. BAF is 15. And CBF is 52. It wants to know ACF. Is there anything else we can fill in this picture?
The left of angle B, like the other angle.
Which is?
52.
Okay. What else? Same thing with A, I agree. Think of the two theorems that we know right now. Do we have perpendicular bisectors or do we have angle bisectors?
Angle.
Yes. I agree we have a right angle here, but can I assume that's an angle or a perpendicular bisector? Why not? It doesn't have congruent marks, right, on the sides. Okay, if it had this, then we could assume it is. Okay, but we do have those angle bisectors. So what do we care about? See this? That point of concurrency, right? So we can assume what about C? What's this line? It's also an angle bisector, so we can assume this is congruent to there. So how can we find that angle in there? Ideas? Why are you thinking that? You're exactly right. Right. We have a big triangle here. What do we know about all angles of a triangle? Add up to 180. Let's simplify this a little bit. What is the total of angle A? 30. What's the total of angle B? 104. So how can we find C?
Add those two and minus what?
Good. So we take 104 plus 30 is 134. Take 180 minus 134 is 46. Okay, 46 is the whole angle of C. So how do I find X? Right, take 46 divided by 2 is 23. So 23 is my X. See how we kind of just used a bunch of things we knew about triangles? Yep. All right, what about that last one there? It says if EF is 3y minus 5 and DF is 2y plus 4. It wants to know what is the distance from F to AB. So what it's looking for is this right here, F to AB, that one. What are we thinking?
Set them equal to each other.
Why do you say that?
Because it's the concurrent of angle bisector.
Right, we have two angle bisectors and we have that point of concurrency. So what do we know about these sides right here? They're congruent to each other. So we know those are equal to each other, so we set them equal to each other. 3y minus 5 equals 2y plus 4. Then we solve, right? What do you end up getting for y? 9. You do get 9, good. So y equals 9. Is that the answer they were looking for? No, what were they looking for? Right, they're looking for the distance. Okay, so how do I figure out what the distance is? Plug it into one of them. Doesn't matter which one. Nope, which one do we want to do? 2y. So we have 2 times 9 plus 4. What's 2 times 9? 18 plus 4? 22. Good. Let's look at these together. How many of you just go straight to the picture before reading directions sometimes? I do too. Okay. With this right angle right here, just by looking at the picture, can I assume that's a perpendicular bisector?
No.
Why not?
This is the side.
It doesn't give congruent markings, okay? But what do the directions tell us? That they're perpendicular bisectors. So now I can assume what? That the sides are split in half, right? So if this is 5, what is this? 5. Did we just answer number 6? Yes, so RC is 5. AT wants to know this right here. Ideas, what are you thinking? Yep, why can we say it's 6?
Does the distance from the vertices to the point of concurrency be the same?
Because of those, right? Remember, if the perpendicular bisectors meet at a point of concurrency, what do we know about the lines from the vertices to the point of concurrency? They're the same. So if this one right here is 6, what do we know AT is? Also 6. Good job. All right, number 7. Does the directions give us vital information?
Yeah.
Yes. It tells us AP are angle bisectors and BP is an angle bisector. Why does that help us? Why does knowing they're angle bisectors help us?
Because they're going to meet at a point and then the perpendiculars are going to be congruent.
Right, they meet at a point, which means these lines right here are perpendicular to each other.
Which means K is gonna be 5 and then L is also gonna be 5.
Good. PK is 5 and PL is 5. Good. Now it wants the perimeter of APL. This right here. This 13 goes with this side. So we know this side's 13, this side's 5. How do I figure out what this side is? What are you thinking? You could use Pythagorean theorem. However, it should be the same as the other triangle, right? Congruent triangles. Also, remember we talked about equidistant? Okay? If this side here is equal to this side, and we have an angle bisector, remember we can assume these distances are the same. Okay? So, we have all three sides. How do we find the perimeter of that? Add them up. 13 plus 12 plus 5 is 30. Nice job. This lesson talked about circumscribed circles and inscribed circles. Okay, so we're going to talk about both of those real quick. Circumscribed circles versus inscribed circles. Okay, both of these circles have to do with triangles. So I want you to draw a triangle on that circumscribed side. Okay. Circumscribed circles are circles that enclose a triangle. It's a terrible drawing, but it's a circle that encloses a triangle on the inside. Okay, that is a circumscribed circle. Okay, what do you notice about that triangle compared to the circle? What'd you say? It's smaller. Okay, what do you notice about the vertices? Vertices are on the edge of the circle. Good. One more thing. This center of the circle, okay, that is called the circumcenter. Okay. What do you think inscribed circles are?
Oh, there's a circle on the inside.
It's a circle on the inside. Yep. So if I have a triangle, inscribed circles are circles that are on the inside of the triangle. What do you notice about that circle?
They barely touch stuff all the sides.
Touches the sides of the triangle, right? Okay. The center here is called the incenter. Okay. Circumscribed circles have a circumcenter, and inscribed circles have an incenter. Okay.